Hello there. In this video we're going to be discussing my personal favorite type of analysis that can be performed on number sequences. In order to illustrate this idea, I'm going to be introducing a few topics, just in case you are not already familiar with. The first of these topics is the Fibonacci numbers. The Fibonacci numbers has several different applications in several different aspects of real life, including their foundation in number theory. The second thing that we're going to be looking at is modulo arithmetic. So modulo arithmetic. Modulo arithmetic also has several examples. The most common of them probably would be time, which is usually based in base 12 or base 24 arithmetic. The third thing that we're going to be looking at is, of course, geometric representation of number sequences, which can probably be rooted to several different scenarios, my personal favorite being the roots of unity. We're going to be starting by looking at each of these three components and then combining these three into a special number sequence that I personally enjoy investigating, that also has several different interesting properties as well. Alright, so let's start with the basics, in particular the Fibonacci numbers, or the Fibonacci number sequence. So we're going to define the 0th Fibonacci number to be equal to 0, the first Fibonacci number to be equal to 1, and then from here we're going to define the nth Fibonacci number as the sum of its predecessors, n minus 1 and n minus 2, and this of course is going to be true for n bigger than or equal to 2. So if we want to graph or figure out fk for particular values of k, 0, 1, 2, 3, 4, 5, 6, and you can continue onwards if you want. Right? So by definition, 0 and 1 is defined to be equal to 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is going to be 13, and this is going to continue onwards as far as you're interested in studying. Of course, the Fibonacci numbers has several different applications, including their connection to the golden ratio of phi, which is 1 plus the square root of 5 over 2, and also some geometry connections. For example, we consider two unit squares, 1 and 1, and then another square of size 2 by 2. Right? So this is going to be a 2 by 2 block. And then of course we're going to have a 3 by 3 block there, and then a 5 by 5 block there. And then we're going to have an 8 by 8 block there. And then this is going to be a 13 by 13 block, even though it's definitely not drawn to scale, and so on. So clearly these are Fibonacci numbers in their own right. So for example, that is f1, that is f2. So we can look at this in terms of area. For example, f0 squared plus f1 squared plus f2 squared, and so on, up to the nth number squared. So the sum of the first n Fibonacci numbers, so one can find that this is just precisely equal to, if we take for example, if fn is equal to 8, then how can we find the area of this entire box? Well, that's just precisely that particular Fibonacci number together with the next Fibonacci number in sequence. Right? So that's going to be fn and then fn plus 1. So if we write this in more compact notation, we can have that the sum from k is equal to 0 to n of the square of the kth Fibonacci number is just equal to the product of the nth Fibonacci number together with the n plus 1th Fibonacci number. This is of course one of several different properties of the Fibonacci numbers, but there's definitely many more that you can investigate on your own, but this is all I want to introduce for now. Alright, so the second idea that I want to introduce is modular arithmetic. Modular or modulo arithmetic, depending on where you're from. Right? So we say and write that A is congruent to B modulo n if n divides A minus B. Typically, we say that b must belong to the interval 0, 1, 2, 3, down to n minus 1. But of course, by this definition, you can take pretty much b to be any integer, positive or negative. But one can say that this is, say, the principal interval of the values of b. So therefore, we can say, as an example, consider the congruence 12 is congruent to x modulo 7. So if 12 is congruent to x modulo 7, then by definition that means that 7 divides 12 minus x. So what does that mean? So that means there exists some integer k such that 12 minus x over 7 is equal to that integer, right? Because that means 7 goes in there an even number of times. So that means 12 minus x must be equal to 7k, or we can rewrite that instead as x is going to be equal to 12 minus 7k. Clearly, if we want this value x to be in the interval 0, 1, 2 down to 7 minus 1, which is 6, then we should be choosing that k be equal to 1, right? If k is equal to 1, that means x must be equal to 12 minus 7, which in this case is going to be 5. That means 12 must be congruent to 5 modulo 7, right? And we write 12 is congruent to 5 modulo 7. Now there is another way of figuring this out using long division, because remember that 12 can be represented as 7 times 1 plus 5. So what exactly is this? Well, 7 is represented as the quotient, and 12 is usually represented as the dividend, and 1 represents the, what is this? So that's the quotient, that's the divisor, and this is the remainder. So if we write this in long division form, 7 divided into 12, we know 7 goes into 12 one time, 7 times 1 is 7, and then 12 minus 7 is going to be 5, and that's the remainder, right? So dividend, divisor, quotient, remainder, right? So we can of course write this as 12 is equal to 7 times 1 plus 5. Of course, there are several different theories associated to this, for example, the Euclidean algorithm. Again, we're not going to get into these details. This is the only thing we need for this discussion. The next thing I want to mention is something that a lot of young people don't really usually see in their study of mathematics, and that would be the geometric nature of numbers. For me personally, I did not really experience this until probably later calculus or maybe even complex analysis. And one of those examples that sort of enlightened me on the beauty of mathematics would probably be the roots of unity. Right? So what are the roots of unity? So let us assume we want to solve the equation z to the power of 5 is equal to 1, where z is some complex number. So one can find that there are exactly 5 solutions to this polynomial equation, and that's just as a direct result of the fundamental theorem of algebra. So where are these solutions and what are they equal to? So if we were to look at the unit circle, right? So it's trivial to see that this point here, so let's assume this is the real part of z, and let's assume this is the imaginary axis for some complex number z. The point 1, 0 clearly is a solution to this equation because 1 to the power of 5 is equal to 1. So where are the other 4 solutions located? So the other 4 solutions are located on points on this unit circle, right? So if we were to connect all these points, then you're going to get a shape. So what shape is this? Assuming that I'm actually good at drawing, this would be a regular. So in this case 5, that would be a regular pentagon. So if we actually want to figure out, okay, well, what exactly is this number equal to, we can actually just approach this in the geometric perspective by calculating that theta angle. So what we're doing is we're partitioning the entire circle, 2 pi, in pieces of 5. So if I actually want to know what that number is, right, this number here, I'm going to call that, say, omega. That means omega is going to be equal to cosine of 2 pi over 5 plus I sine 2 pi over 5, right? And that's going to be the first one. And if you sort of want to generalize this, I can put a k here, and we can say that k is equal to 1, right? So if I want each of these, for example, if I call this W0, W1, W2, W3, and W4, let k range from 0 to 4, and that would be the complex representation of W, right? So therefore, if z to the 5th is equal to 1, that means z must be equal to omega k, where k ranges from 0, 1, 2, 3, and 4. And if you were to plot these on the unit circle, you get a regular n-gon, which in this case is a regular pentagon, which to me is extremely beautiful because it connects complex numbers to the realm of geometry, which to some sense is not too surprising once you know enough about trigonometry, but to me, at least when I was a student, found this to be extremely beautiful. All right, so this is where we're going to begin to have a little bit of fun and a little bit of experimentation with all these concepts. So as I said before, I'm going to be primarily focusing on the Fibonacci number sequence, but perhaps you might have another number sequence that you might be more interested in. For example, the law numbers, the Bell numbers, the Leyland numbers. There's several different types of number sequences that have a variety of applications. So you can actually perform this same exact analysis that I'm going to be performing with whatever sequence you want. So if you want, you can sort of follow along with me with whatever sequence you're doing and see what kind of interesting results you may come up with. Right, so again, we're going to be considering the Fibonacci sequence, which is going to be 0, 1, 1, 2, 3, 5, 8, 13, and so on, right? Let's just do a couple more numbers, say 21 and 34, right? And of course, this order does matter because 0 is going to go to 1, 1 is going to go to 1, 1 is going to go to 2, and so on. So this order is unique. So what I'm going to do is I'm going to consider this number sequence modulo 2. So remember, the numbers modulo 2 is only going to have two possible numbers, 0 and 1, right? So 0 is congruent to 0, 1 is congruent to 1, 1 is congruent to 1, 2 is congruent to 0, and so on. So pretty much in modulo 2, all the even numbers are congruent to 0, and all the odd numbers are congruent to 1. So 3 is going to go to 1, 5, 1, 8, 0, 13, 1, 21, 1, 34, 0, and so on. Now, what you may begin to see if you go longer is you may see that there is a pattern, right? So this pattern is what we refer to as the Pazana period. The Pazana period. And Pazano is named after Leonardo Pazano, which I believe is an alias for Leonardo Fibonacci, right? So different last name, but same person that we're referring to, right? But this is referred to as the Pazano period. And I'm going to denote this as pi with a double bar above it, right? So the Pazano period of order n, so n is going to be referring to this modulo that I'm going to be working with, is the length of the period for the Fibonacci numbers, the Fibonacci sequence, modulo n. Right? And we clearly see, and we can prove by induction, if we may, that the Pazana period of order 2 for the Fibonacci numbers is going to be equal to 3, right? And again, I said you can use pretty much any number sequence, and you can sort of follow along to figure out, say, okay, what is the Pazana period modulo 2 for, say, the Lucas numbers, for example, right? All right. All right, so let's just do another example to sort of illustrate how to calculate the Pazana period, at least through the brute force approach. So the next one we're going to be doing is going to be modulo 3, so we're going to find Pazana of 3. So let's see, what's the Fibonacci sequence? So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 87, and then we can continue on if we want. That should be 89. 89. All right, so how are we going to calculate these numbers? So remember, modulo 3 means what is the remainder when you divide 3 into each of these numbers, right? So clearly, 0, 1, and 2 are just going to be themselves. That's one of the basic properties of modulo arithmetic. So this is going to be 0, this is going to be 1, this is going to be 1, this is going to be 2. 3 divides evenly into 3, so that's going to be equal to 0. 3 goes into 5 once with a remainder of 2. 3 divides evenly into 8 with a remainder of 3 divides evenly into 8 2 times. 2 times 3 is 6 with a remainder of 2. 3 times 4 is 12, and that's the biggest multiple of 3 that goes into 13 with a remainder of 1. And you can continue this pattern if you want. So that's going to be 0 because 3 goes into 21. That's going to be 1 because 3 goes into 33. This is going to be 1, this is going to be 2, and you can continue onwards if you desire. So do you start to see any patterns here? Let's see. So we have 0, 1, 1, 2, 0, 2, 2, 1. And then we have 0, 1, 1, 2, and actually you will be able to see that there actually is a pattern here. So what do we have here? So we have 1, 2, 3, 4, 5, 6, 7, 8. So therefore one can verify the Pazana period of 3 for the Fibonacci numbers is going to be equal to 8. Right? All right, so how is a better way to visualize this, and how can I sort of bring in the geometric nature of these patterns? So I'm going to introduce the concept of modulo polygons. So modulo polygons. Okay? So modulo polygons, so I'm going to be looking at the unit circle, sort of like the roots of unity. So let's assume we're interested in the modulo polygon of order 2 for the Fibonacci numbers. So I'm going to be considering the numbers 0 and the numbers 1. So the modulo polygon of order 2 is just going to be pretty much a line segment. So 0, so what are my sequence numbers? So we have 0, 1, 1, 2, 3, 5, 8, 13, and so on, right? So remember that 0 is mapped to 0. 1 is going to be mapped to 1, so I'm just going to draw a vector in that direction. 1 is going to be mapped with 1, so it's not going to go anywhere. 1 is going to be mapped, 2 is going to be mapped to 0, so it's going to go back over here. And then we're going to go to 3, which is going to be mapped to 1, and so on, right? So pretty much all of the vertices are connected, right? All vertices are connected, right? Now, for the modulo 2 case, this is not that interesting. Once we increase the value of m, then it's going to become a little bit more fascinating, at least to me. So now let us consider the case when n is equal to 3. So when n is equal to 3, that means we have 3 numbers of interest, right? We have 0, we have 1, and then we're going to have 2 over here. So if we were to connect these vertices, you should get a triangle, right? So again, if we go back to the modulo 3, 0 was going to be mapped to 0. 1 is going to be mapped to 1. 1 is going to be mapped to 1. 2 is going to be mapped to 2, so remember, we're going from 0 to 1, 1 to 1, and then we're going to go 1 to 2. And then now we're going to go from 2 to 3, and remember 3 modulo 3 is going to be equal to 0, so 2 is going to be mapped to 0. And then we go to 5, well, 5 modulo 3 is going to be 2, so then we're going to go back to 2, and so on. But actually, we're going to stop here because, again, all vertices are connected. Right? So this is going to be the property that I'm going to be focusing on in terms of this video. You may even want to consider the property where all vertices are connected in both directions, right? So it's possible under some sequence, right, that you have a triangle that only goes in that direction, and that direction, right? So, or possible in those directions or those directions, but in one of the edges, it's only going in one direction. So you may want to consider that type of vertice connection or that type of graph, right? All right. All right, so let's just define a terminology that I'm going to use here. So we define a modulo polygon to be complete, or one can say 1+ way complete, if all vertices are connected, right? And you can extend this to say 2+ way complete or 2-way complete. That's the case where all the vertices are connected in both directions. So one is going to go to 0 and 0 is going to go to 1, and same thing for all of the others. Okay, so now what I'm going to do is I'm going to increase this up by 1 order. In particular, n is equal to 4. Now this is where the game begins to get a little bit interesting. Alright, so I'm going to again consider the Fibonacci number sequence modulo 4. So this is going to be 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Right? So calculate these Fibonacci numbers modulo 4, and what will you get? Well, you're going to get 0, 1, 1, 2, 3, 1, 0, 1, 1, 2, and you can continue onwards if you want. All right, so what is going to be the Pazana period for order 4 for the Fibonacci numbers? Well, we should be able to clearly see that we're going to start getting a pattern after 6, right? So the Pazana period for 4 is going to be equal to 6 for the Fibonacci numbers. Okay? So let's look at the modulo polygon for this particular modular sequence, right? So we're in modulo 4, which means we're going to have 4 vertices in our polygon. One corresponding to 0, one corresponding to 1, one corresponding to 2, and the other corresponding to 3. Right? So let's construct the polygon to see what it looks like. So 0 is going to go to 1, 1 is going to go to 1, 1 is going to go to 2, 2 is going to go to 3, 3 is going to go to 1, right? And then 1 is going to go to 0, and then the pattern continues, right? So this graph is not complete, right? This graph is not complete. Now, why is it not complete? Well, it's not 1+ way complete, at least, right? Because we're missing the direction from 3 to 0, and we're also missing the direction from 2 to 0, right? Because, in essence, this picture isn't pretty, right? That's pretty much what a non-complete graph represents. Maybe it looks pretty to you, right? But it's not complete, at least by this definition. Right, so for the modulo polygons for the Fibonacci sequence, in terms of completeness, or 1+ way completeness, right? So 1, 2, 3, 4, 5. So we've considered 1, 2, 3, and 4. 1 is complete trivially, 2 is complete, that's our line, 3 is 1+ way complete, and 4 is the first one that is not, right? So is there a way to sort of figure out quickly whether the modulo polygon for the Fibonacci sequence is complete, or 1+ way complete or not, right? So clearly, one can find, so if one knows the Pazana period of order n for the Fibonacci numbers, or whatever number sequence you're working with, then one can construct, or then the modulo polygon, but not the modulo polygon, can be constructed using, and let's assume that the Pazana period of order n is equal to, say, k, right? Then in that case we can use k calculations, right? That means we do not have to list an infinite number of Fibonacci numbers in order to construct the modulo polygon for this particular sequence. All we need to do is just go up to the Pazana period, because then it's going to reiterate past that. It's going to have the same exact trace, if you may, right? So the graph isn't going to change. So as long as you know the Pazana period for whatever modulo you're sort of working in, the modulo polygon can be constructed, and then we can determine whether all of the vertices are 1 plus or two-way connected in that state. All right, so since we pretty much have the general idea of what we're calculating here, clearly this is an algorithmic process. So using computers to pretty much generate these polygons is definitely beneficial. You can easily plot how many points using cosine and sine plotted on, say, the unit circle. And then, for example, we can do a line segment from one Fibonacci number modulo n to the next Fibonacci number modulo n, and that will create the line segment. And of course, if there's a line segment connecting all of the vertices, then we know that that modulo polygon is, of course, at least 1 plus way complete, right? So pretty much what I have going on here is exactly that. And since I do not necessarily know the closed form of the Pazana period for an arbitrary natural number n, I'm pretty much going to go up to an arbitrarily high number of iterations. Remember, once we pass that Pazana period, the figure is pretty much going to stack on top of itself, so it's not going to introduce any noise or errors in terms of the polygon that is going to be constructed. So I'm going to start by looking at just a couple of the modulos just to make sure that this works. So if we run this for modulo 2, we of course get the modulo polygon that should be a line. So if we look here, this will be the modulo 2 polygon, and since of course all vertices are connected, this is 1 plus complete. So if we increase this number up to, say, 3, and then run this, we then have the modulo 3 polygon, and since all the vertices in this graph are connected, this is at least 1 plus way complete. So remember, once we hit 4, then we started having a bit of issues, right, in terms of completeness, right? So here's our modulo 4 polygon. Clearly we do not have vertices 0 connected to 2 and 3 connected to 0. Therefore, this is not a complete modulo polygon. Now let's look at a few modulo polygons that we did not calculate by hand, for example 5. Right? So take a guess. Do you think the graph for the modulo polygon is at least 1 plus way complete? So let's take a look. So here is our 1 plus way polygon for modulo 5. So clearly each of the vertices are connected to one another. Therefore, the modulo 5 polygon for the Fibonacci sequence is at least 1 plus way complete. Now remember, why do I keep on saying 1 plus way complete? Because, say, vertice 0 to 1 may not be the same direction as 1 to 2, because these vertices are connected in an ordered fashion, right? There's linear ordering on these vertices, and it's not necessarily two-way, right? So the modulo 5 polygon is complete. So what about 6? Do you think 6 is going to be complete? So here is our modulo 6 polygon. Definitely a pretty picture, right? But is it complete? The answer is no, because we clearly see that vertice 0 is not connected to 3, right? But it still is a pretty picture. I think most people maybe would agree with that. So let's change this to 7. Do you think 7 is complete? So, okay, well, not necessarily, but we do have this little opening, right? So 0 is not connected to 3, 0 is not connected to 4, 0 is not connected to 2, and 0 is not connected to 5, right? There's a few other, I believe those are the only things that are not connected. No, we also have this vertice not connected to that vertice, right? So we definitely do have some issues with modulo 7, but nonetheless, it is not complete, right? So let's shift this to 8. Is this going to be complete or not? Answer is no, right? Now remember the graph for 4 pretty much had this very weird truncated pattern to it, right? And we can bring back 4 just in case you have forgotten it. So we had this type of truncated behavior, right? So let's shift up to 9 just to see what that looks like. Right? Definitely a cute little picture, but again, this is not complete. Let's look at 10. So 10, again, very beautiful picture. So just based on looking at this, do you think this is complete? So hopefully you said the answer is no, right? Because this vertex here, 0 is not connected to the one on the opposite end, 5. That is the only one that is not connected. Similar to the modulo polygon of order 6, right? Remember the order of modulo 6, everything was connected except for 0 and 3. Now, did we have the same pattern for 8? No, right? But we do have that beautiful little pattern for 10 and also 6, right? So 10 and 6 both generate modulo polygons, which are almost complete except for 0 and n divided by 2, right? So we definitely do have some symmetry associated to polygons that aren't even complete, right? Which to me is very beautiful, right? I mean, it's not really complete, but maybe we can call it, say, weak complete or semi-complete, where we have sort of a weaker condition on that definition, where all of the vertices are connected except for 0 and n divided by 2, right? That would be a reasonable definition because definitely these structures are nice in nature. So just for curiosity, let's just go up to 11, right? Which of course is a prime number. And we get some jagged nonsense. There's lots of vertices that aren't connected here. Let's go up to 12, which is an even number. Also jagged, not very pretty, so let's pretty much ignore him. Let's consider 13, also prime. We have this, a little bit more nicer than 12, but of course not complete. Now remember, this might not be the modulo polygon because notice I'm only going up to 100. So if this is not the modulo polygon, that implies that the Pazana period is larger than 100. So what we can do is just increase this number of iterations up to 1000 to see if that changed any. Aha! So now we have this picture. And one can probably argue that yes, this picture is actually quite beautiful, right? And notice how that that circle, that little polygon in the middle is pretty much forming a circle. Probably as I increase n to infinity, we get that little circle generated, right? So here's a cute little question. As n goes to infinity, what happens to the radius of that that circumradius for that polygon? What does it go to? Just a cute little exercise, right? So is this complete? It appears so, right? So I'll leave it to you to figure out whether that is or not. So let's go back to 12 and 11 just to see if those actually were more complete than what we thought they were, right? So of course 12 is a little bit more jagged just as it was before, and also 11. Let's see what we have here. So 11, okay, 11 is actually not too bad, right? So it's these even numbers that are actually causing the issues, right? 4 was a big issue. 6 wasn't a total big issue, but it wasn't complete. 8 was an extremely bad issue, right? So remember 8. 8 was that little broken piece, right? There it is. But 10, of course, was not complete, but we were thinking about, maybe we can call it semi-complete, right? Because we're missing the vertice from 0 to 5, right? And now, if we go up to 14, what do we have? Well, we have a modulo polygon, and probably we're missing a couple things, right? So we're clearly missing these two here and these two here. So it's possible that, oh, we're also missing a few on the sides. So is it possible that maybe this iteration isn't high enough? So let's see if this generates a complete or semi-complete modulo polygon. So this may take second or so. So here we are, and again, this has not changed, right? So either this is the modulo polygon or the Pazana period under modulo 14 is larger than 10,000, right? So either one or two of those, either one of those must be true or false, right? So clearly, definitely not a bad looking graph, but it's not complete, right? So these even numbers are definitely causing some issues. And here's a little question that I haven't figured out. Well, I can propose a couple corollaries or conjectures of why that is, but maybe you want to investigate on your own and then leave it in the comments of what you think, right? So what do you think is going to happen when I go up to, let's go up to 21 just for fun. So again, this is an odd number. Most of the odd numbers, pretty much all of the odd numbers so far, have generated complete or semi-complete modulo polygons. So what do you think is going to happen for 21? So once you generate the modulo polygon for modulo 21, you get this very, very beautiful picture, right? I think this is very attractive in terms of geometry, right? So is this complete? I leave it to you to decide, right? But I believe, just by looking at it, most likely yes, right? So what about 22? Do you think 22 is going to be complete? Probably not. Even numbers are usually the troublemakers, at least in this problem, right? So here we have a modulo 22 polygon. So of course, notice we have a couple blue dots that don't even have edges connected to them, right? Okay, well, what does that mean? Well, it's possible that the Pazana period is larger than 10,000. So let's increase this by another magnitude of 10 and see what happens. So after about 5 or so minutes with my silk computer, again, we get this representation for the modulo 22 polygon. So again, a few of these vertices are not connected. So either this is the modulo 22 polygon, which clearly is not complete. I mean, the vertices aren't even touching a couple of these values. So we may want to create a more weaker definition of this modulo polygon because not even the vertices are connected, let alone connected to each other, right? Right, and that's iterated over 100,000, right? So most likely the Pazana period for modulo 22 should be less than 100,000, at least intuitively to me, it should be. All right, so let's knock this down a couple magnitudes in order to explore a little bit more. Let's go up to 27, which of course is an odd number. Odd numbers are our friend, right? So let's run this to see what happens. And let's look at the modulo polygon to see if it actually is nice. So what do you think it's going to be? Is it going to be complete? Is it not going to be complete? What do you think? Oh, look at that. Isn't that gorgeous? Right? So here we are. We have our beautiful picture. So is this complete? My answer is I believe so. Right? So I'm leaving a few questions open here. But actually, maybe not. I do believe it is, though complete. Maybe the Pazana period is larger than 1,000. So let's just give that a go just to see if my result changes. And no, not really. I don't see much change here. Pretty much what I'm looking at is pretty much the density distribution around each of these vertices. Pretty much notice that all of these here don't have really any white space, but this has this little vector that's sort of missing here. This is missing a vector, this is missing a vector, this is missing a vector, and this is missing like two vectors, this is missing one, right? But I believe I definitely cut off a couple here, so it's possible that the Pazana period for 27 is larger than 10,000. Right? But at least through these explorations, we can see that none of the even orders of modulo polygons are complete. Therefore, if we want to investigate what is the least mega number, for example, a number bigger than 1 million that has a complete modulo polygon, 1 million definitely is not it. So here's a question. Do you think 1,000,001 is a complete modulo polygon, right? So, or moreover, if it's not 1,000,001, what is the least mega number that has a complete modulo polygon? I'll explore this on my own time, and maybe even I already have that answer. But anyway, I hope this gives you some investigative tools in order to explore your own favorite sequence. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.